So I think now we're going to get started. All right, so the correct answer to this question is astrology. It's not a field of physics. Astrology is like a pseudoscience. That's like the horoscopes and all that. That's just a pseudoscience. Quantum mechanics and electromagnetism, no one chose those. You guys are familiar with those. Cosmology is studying about the origins of the universe and how we came to be, right? So that's more of a field of physics, cosmology. And astrology would be the not a field of physics.
An answer for this question is actually quite interesting because we don't know if light is really a wave or particle. These are all just the properties it's shown us. We don't know its true nature. But I think it's safe to say that it is both wave and particle.
We covered this one in our first lecture, the double slit experiment 1801 by Thomas Young. If you need to access the lecture slides, you can do so at V Clubs, along with our meeting recordings.
I think your image just spoiled it.
So this is a true question. This is a fast 10 seconds. We do the true false in 10 seconds. And so this is a true statement. And diffraction was used in the double slit experiment, which refers to light's behavior when it's going through like an edge or a slit, right? And so it makes a constructive and destructive interference pattern. I think you guys can see that photo over here, which is an example of the constructive destructive interference pattern in the double slit experiment. I don't think we need to explain this one. This is an 8 for 8 double slit experiment, just demonstrated light as a wave, not a particle. All right, so for this question, you can see in the media, we were demonstrating the atomic spectra. If you remember this one where we were exciting the hydrogen gas, and we're taking the light from that gas and we're reflecting it right here using the prism. And so we were able to see that light comes in specific chunks with definitive energy, was the key concept here with the atomic spectra. And we covered this in great detail in our second lecture of light coming in chunks with definitive energy. And this is a true statement.
Yes. So the part about black box radiation is that the black box it not only like absorb. So the reason it's called black is because usually we think black as it absorb all the lights, but black body black body also needs to radiate energy, because if it only absorb radiation, it will soon become hotter and hotter, and soon it will not become a black box, simply because there are too many energies, too much energy.
And for the blue option, electrons releasing from a metal by the electromagnetic radiation, that's the photoelectric effect. All right. So for this question, it's in fact Planck's law, as we covered before. And so here, if you remember this graph right here, so this green one's like the right one, this is Planck's law. And if you remember, the Rayleigh-Jeans equation worked for very low values of the frequency. You can see it's kind of matching for very low values, the red one. And the blue one, which is Wien's law, works for much higher values instead, right? And so Planck's was the correct one in this case. And there's no such thing as Newton's law of black body radiation. Right, this was a little bit more confusing. So this is an example of the photoelectric effect right here. So here you can have the electromagnetic radiation. You have the sun here, right? It's hitting this positively charged plate. Electrons are flying off this plate to the negatively charged plate, right? This plate is positively charged. This one's negatively charged. It's flying from plate to plate, which makes this one positive charged and this one negative charged. And so you can see there's this current meter on the right, the multimeter, and it's going to measure that current, right? Because you have some electrons here and you have a positive charge here. So there's like a potential difference here in energy. So remember that the electrons are flying off, which essentially creates your current, according to the photoelectric effect. All right, so for this question, energy is determined by the amplitude of light in photoelectric effect. That is a false statement. It's actually determined by the frequency of light in photoelectric effect.
Amplitude only
And this
like
is just the photoelectric effect.
amplitude only describe like the number of photons, the intensity of the light. It does not depend the energy level of one photon.
So yes, this one is 9 for 9. It takes work to get electrons off a piece of metal in the photoelectric effect, right? And you can see this is actually an example of a problem they conducted this at MIT right here. It was in one of their chemistry courses, I believe. But here you can see that they want the maximum kinetic energy of the ejected electrons once the electrons are ejected from this gold. And so what you do is you just take the difference here, right? 8 minus 5.1 gives you 2.9, which is answer choice 2. So the other three, they are applications of the photoelectric effect. Star temperatures is more in regards to black body radiation and the astronomy applications of black body radiation, while the others are applications to photoelectric effect. Night vision goggles is a pretty cool application for photoelectric effect. So as we covered in our third lecture on wave-particle duality, we were seeing that the connection between the black body radiation and photoelectric effect is Planck's constant. So this is an example of a plot. Right here, this was Einstein's data regarding the photoelectric effect for different metals. Here you have like rubidium, you have potassium, you have sodium. And so here you can see the slope of this is actually Planck's constant, right? Which was a constant when Planck was analyzing the black body spectrum, right? He felt the need to put a constant in there, and that was Planck's constant. And so there's a connection right there between the black body radiation and the photoelectric effect, which is very relevant to quantum mechanics. And there are two answers for this one. We didn't exactly cover this one. This is a good question, though, for quantum mechanics. All right. So for this question, this also touches a bit on wave-particle duality. So in certain experiments, we either think as a wave or as a particle, right? So waves have a more precise momentum, whereas particles have a more precise position, right? And so these are the two true statements. And so we choose like one of those pieces of information to retain, depending on how we think of the thing in question, essentially, in the experiment. And it relates a little bit to uncertainty, which we might cover in the future. Quantum mechanical uncertainty.
We will.
So this is false. So this is about the fictional stories in physics. If you remember that slide, Einstein never actually helped de Broglie with this thesis on the matter wave, but it's just an interesting fictional made-up story. That's a common misconception. This is 9 for 9. So in the electron slit experiment, you see this pattern right here, which shows that the electron is actually interfering with itself when it goes through the slit. Even if we throw like one electron at a time, it still creates this wave-like pattern, right? And you think of electrons as particles, but it's creating this wave-like pattern, right? And so we see that the only possibility is that the electron is actually interfering with itself, kind of like a wave, when it goes into the slit. And so this is actually very remarkable, very groundbreaking idea, that the electron can actually interfere with itself in these slit experiments. This is just feedback for the future. Especially that nobody hated it. We will try to make a few more improvements next time. If you like a recommendation for other activities, then you can hit that yellow option, and then you can put that like in the chat. All right. So for the person who has a recommendation for the future, please put that recommendation in the chat. We'd like to know more about your recommendations so we can keep improving the club and hosting cool review activities. Just give you a little bit of time to think about this one. Would you be interested in going over the problems in SAT or AP Physics next class and try to do a little bit of problem solving with physics? All right, so we have a good amount of people pretty open to these problems. So I'll probably try to incorporate some of these AP or SAT physics problems, a handful of those. All right. So those are the results for our first Kahoot. So with the time that's left, I think I'll stop screen sharing now. So those are the results for the first Kahoot. I'm probably going to send the questions and solutions after the meeting. So I hope you guys enjoyed the Kahoot. We're going to leave this time for questions. Less questions because we covered a lot over the last few meetings and we didn't really have much time for questions. Also, you can redirect other questions to vchsphysics@gmail.com. Put that in the chat. So we are open to any questions. Myself, Alan, or Alex, we'll try to answer your questions.
I think we have 7 more minutes, so we can move on to the slides and just chime in whenever you want. Unmute yourself or put stuff in the chat. So I do have a slide here. All right, so we have we have a website. It's called Particle Adventure. It's introduced by Jenna. Would you like to give us some information on that?
Yeah, sure. So this is just a website that I found a few days ago called the Particle Adventure. If you're interested in like particle physics, this gives a good introduction to the Standard Model, which is just all the elementary particles and the 4 fundamental forces. And it also has sections on the Higgs boson, particle accelerators, and some other mysteries in particle physics. So if that's something you're interested in, then this is a really good resource and it's really cool. Yeah.
It has a lot of activities. Yeah, it's pretty cool. And Molecular Workbench is also a good resource for anyone who wants to do some virtual hands-on stuff. And so next we have our physics photo of the day. And this is also taken from the high school physics photo contest. This is a student took a photo of a cloud chamber. It's a time-lapse photo. So you see the accumulation of well, first we need to go through what is a cloud chamber. So there's a radioactive material in here, and in the cloud chamber, it's sprayed with alcohol vapor. So this radioactive material will give up alpha particles. They're ionized. They are very they are a helium particles with only 2 photons but no electrons. So they have this charge and they're moving very fast. So along the way, they would ionize the alcohol vapor atoms they encounter. And for these atoms, when they are ionized, they become a center for condensation. So that's when you can observe, because of the condensation occurs, you observe white solid alcohol trails. So you can actually see the radiation. So you can find a very cool video in the slide, and it's pretty cool. thing to check out.
So we are going to talk about, briefly explain Bohr model, which if you take chemistry or chemistry honor or AP Chem or regular chemistry, you will learn about it. So so at that time, physicists faced a problem on explaining the hydrogen emission spectrum, which is when you give hydrogen atom electromagnetic wave, it emits a strange spectrum, which the light is not continuous. It is spreading from the wavelength of light varies and is not continuous at all. So Niels Bohr, one of our greatest physicists at that time, come out with an atomic model that says that there are different energy levels of atom's orbit, and when electrons jump from one orbit into another orbit, it will takes in energy, and when it falls back to its inner most inner orbit, it will release energy. And the emission spectrum is just when the electron drop back from a higher spectrum, the energy it released becomes the spectrum. So this also uses an idea that this uses an idea of quantum, because energy is explained as a certain value, not a continuous value. So but the question about this model is that the model only describes the spectrum of hydrogen atom, which has only one proton and one electron. It cannot accurately describe more complicated atoms. So about the contribution, so Bohr model is the first model that tries to explain atomic models through quantum physics approaches. So it acts as an answer sheet since it correctly described the hydrogen atoms. Then if other atomic models come out, if their answers matches the answer of Bohr model on hydrogen atoms, then you can say that the new model is correct. So the Bohr model did usher in the idea of quantum physics, but it has limitations. So in order to make an atomic model for almost all atoms, so anything concerning classical physics ideas must be abandoned. So, but nevertheless, it shows that quantum physics is applicable is applicable on the atomic field. So matrix mechanics. I think we can leave this next class. It's already 48.
Right. So next class, we just went through Bohr's model. We don't have much time left. There are more different models that we can explain, and there will be a introduction to Schrodinger's ideas. And here's He's equation. You might have seen it in chemistry class, but we will understand it more through next time. This is a He's wave function is also yet another model closely related to the matrix equation. Yeah, so I think we'll leave it for next time, and hope that started your day well. And if you feel like Kahoot was fun, that's great. If you didn't get all of them right, it's just for fun, and hope that's helpful conceptually for your understanding of physics. And please just contact us through email and email us any suggestions you may have. Yeah.
Nice job, Alan, Alex, Rohan. Good job.
Thank you.
Thanks, guys.
Thank you.
Bye, guys.
Thank you, Alan. Thank you, Alex. Thank you, Jenna.
Thank you, Rohan.
Have a nice day.
See you
Have a nice
soon.
day.
Bye, Mr. Norman.
See you, Mr. Norman.
Thank you, Mr.